Everybody, thank you for coming in the early morning. And at first, I would like to thank organizers for giving me a wonderful opportunity to give a talk here. And I'm going to talk about the effect of congenital blindness on the functional organization of the lateral occipito-temporal cortex. In the field of developmental psychology and neuroscience, it is widely assumed that vision plays a critical role in the development of social cognition. For instance, neonatal imitation of facial expressions and the infant's ability to imitate others' hand gestures are considered to be critical to develop the ability to mentalize or inferring others' mental state. Then what happens if vision is deprived from birth? There's a longitudinal study in which researchers compared autistic trait of individuals with sighted individuals with ASD, autism spectrum disorder, and congenitally blind children. When they were 6 or 7 years old, the autistic trait of both groups were comparable, such that blind children were misdiagnosed as ASD. However, 9 years later, autistic trait of congenitally blind children was reduced such that they were no longer considered as ASD. This result indicates that vision plays a critical role. However, non-visual sensory modalities can contribute to the development of social cognition and overcome such delay. Given this background, we would like to ask if brain networks for social cognition can develop without vision or not. As you may know, there are distributed sets of the brain regions involved in social cognition. And here, I would like to focus on one region and its connected network called extrastriate body area, or EBA. This region has two interesting characteristics. First, this region is selectively responsive to observed body parts as compared to observed other categories of objects. Second, this region is also active during the execution of your own action as compared to rest. So this region seems to receive two inputs, signals of observed actions and executed actions. We previously demonstrated that these two signals seem to be interactive with each other in the EBA. In this study, participants were asked to execute some specific finger gestures and subsequently observed actions of others. In one condition, observed actions and executed actions are congruent, or the same, and in other conditions, these two actions are different. And when we compare these two conditions, we observe the effect of congruency in the extrastriate body area. Furthermore, when we did the same experiment on the individuals with ASD, such congruency effect was reduced, which is consistent with the idea of the involvement of EVA in the social cognition. So, in the EBA, signals of executed actions and observed actions are interacted with each other. If this is the case, even without vision, signals of executed actions may be sufficient to develop the functional organization of EBA. So how can we test this? Because born-blind individuals cannot see objects. So we used haptics instead of vision to examine the functional characteristics of EBA. We previously demonstrated that the EBA in the sighted individuals can show similar object preference regardless of sensory modalities, even whether the vision is used or haptics used. In this study, we used bottle as a control object. And as compared to the control object, perceived hand and perceived foot showed higher activity. However, in this study, we didn't examine blind individuals' brain. So in the next study published in 2014, we tested the functional characteristics of the EBA. In this experiment, we recruited 28 blind individuals and 20 sighted individuals. Among 28 blind individuals, 18 were congenitally blind or born blind individuals. In this experiment, we used 3 different categories of objects using 3D printers: hand shape, pot, and toy car. And each object category contained 4 different exemplars. So the participant's task was to identify these objects at exemplar level. For instance, if this object was presented, then the subject's task was to press a button corresponding to A. Since this experiment is a haptic, you need to do some primitive work. So experimenters are standing by the subjects and presented the object each by using a slider platform. Born blind and sighted individuals conducted the following tasks. First, both of them conducted the haptic identification task as I explained. In addition to this task, sighted individuals conducted 2 different tasks: visual identification task and EBA localizer task. Visual identification task is identical to haptic identification task except for the trial duration and the number of trials used. But in both tasks, we are interested in comparing hand-related activity with the activity during the perception of the other categories of objects. And finally, sighted subjects also conducted EBA localizer task. We used classical mass univariate analysis using SPM and SNPM. So here's the result of the sighted individuals. This is a result of the sighted vision, and this is a result of sighted haptics, and this is a conjunction or overlap of vision and haptics in the sighted individuals. Light blue color shows the location of EBA. And this EBA seems to be a bit larger, but this is a group level result. So as can be seen from this result, there's a substantial overlap between vision and haptics and EBA. Then what happens to the blind? This is a result of the blind individuals, and this is the same figure as previous slides. And there are 2 points worth mentioning. First, anterior and superior part of the EBA shows hand-sensitive activity regardless of the group. On the other hand, or second, infero-posterior part of the EBA showed a difference in hand-sensitive activity. So in order to further examine this point by conducting stringent analysis, we did the following analysis. First, we conducted a conjunction analysis of sighted haptics, sighted vision, and congenitally blind haptics. So in this analysis, we excluded blind individuals with visual experience from the analysis. Nevertheless, we observed activity, hand-sensitive activity in the supramarginal gyrus as well as anterior and superior part of the EBA. So this result indicates that these regions are supramodal regions. Then what happens to the inferior or posterior part of the EBA? In order to test this, we conducted the 2 analyses. First, we simply compared blind individuals and sighted individuals. Second, we are also interested in how the length of early visual experience affects the functional organization of LOTC or EBA. So we conducted a simple regression analysis with the age of vision loss as a predictor. The first analysis showed reduction of hand-sensitive activity in the blind individuals in the infero-posterior part of the EBA. The second analysis showed another part of the inferior EBA showing hand-sensitive activity correlated with the length of early visual experience and also relative performance accuracy. So to summarize the result to this point, there seems to be a different vision dependency within the lateral occipito-temporal cortex. So in the next analysis, we were interested in how these regions, subregions, are functionally connected to the other regions. In order to address this question, we use the classical psychophysiological interaction analysis to examine the task-dependent functional connectivity. This is a result of sided haptics. When we use this seed, supramodal EBA seed, for PPI analysis, we found a PPI effect in the posterior parietal lobule and sensory motor cortex, as well as occipito-temporal cortex. And this pattern was highly similar between two different seeds, supramodal seeds and vision-dependent seeds. On the other hand, when we did the same analysis with the blind brain data, there were some differences. So when we used supramodal EBA of the blind individuals, this region was functionally connected to posterior parietal lobule, but as well as large areas of occipital cortex. However, when we used vision-dependent EBA of the blind, there's no such PPI effect was observed. And these observations were further confirmed by direct comparison of the seed-related PPI effects. So we confirmed PPI effect in the occipital cortex and posterior parietal lobule. And we also confirmed common PPI effect between bone-blind individuals and congenitally blind, sighted individuals in the posterior parietal lobule around the intraparietal sulcus. So to summarize, first, superior part of the EBA and anterior part of the EBA and its functionally connected posterior parietal lobule seems to be developed even without visual experience. So these regions form some supramodal networks for the recognition of hand shape regardless of the visual experience. On the other hand, concerning the inferior-posterior part of the EBA, this region not only showed a reduction of hand-sensitive activity, but also its functional connectivity was not clearly observed in this study. So inferior part of the EBA seems to change its function such that it's no longer used for hand recognition. And it's important in the future to examine what kind of roles this node plays with other brain regions. Finally, though this is not brain mapping, but I would like to introduce one way to use haptic recognition. So one of the issues or problems with blind children, bone-blind children, is to control their facial muscles. Especially upper facial muscles are hard to be controlled, such that sometimes it's hard to express emotions such that others can identify. So in the future, haptics can be used as mirrors between self and others, or self, to learn motor control of facial expressions or other actions. This is the end of my talk, and thank you for listening.